In the hunt to discover what formed the Marianas Trench, scientists now know crust created at the ocean ridge is being devoured somewhere and by something in the Pacific Ocean. They suspect the Marianas Trench is involved. But the proof would come not from the trench, but from these. The Mariana Islands, a chain of volcanoes that break through the ocean surface 200 miles west of the trench. Scientists noticed the island chain mirrors the trench's exact shape. This led them to think the trench was responsible for the island's creation.
If you see pictures of the Marianas Trench, it's curved, and the line of volcanoes that it generates is curved exactly parallel to it.
Geologists believe that the trench formed the volcanoes via a process called subduction. Subduction occurs where two tectonic plates collide. As they grind past each other, the heavier plate is pushed beneath the lighter plate. The descending plate is forced down into the Earth's intensely hot interior called the mantle. It takes with it water and sediment built up over millions of years.
Volcanoes form above subduction zones not because the Earth is hotter there, but because this is where we're taking the water that once was in the ocean. It's taken into the mantle and gets sweated out, causes the mantle to melt, and this magma is what then rises and erupts explosively out these volcanoes.
The water in the sediment forces magma to swirl up and push through the plate above. And when it breaks the surface, it creates volcanoes, like the volcanoes that form the Mariana Islands. It was subduction that formed the islands west of the trench and gave investigators the breakthrough they'd been looking for. Because here, at last, was a process powerful enough to create the Marianas Trench. As the descending plate dives down, it digs into the mantle. Here, the colliding plates form a trench, a giant crease in the ocean floor. It seemed that scientists had finally explained how the trench was formed. There was just one problem. A very large problem. Around the world, subduction zones cause violent earthquakes and catastrophic tsunamis.
We know subduction is happening because of the active earthquakes, and these are the most devastating earthquakes. This is the earthquake that generated the tsunami in Sumatra. Also, the other very large earthquakes in Alaska and Chile.
But the Marianas Trench, the deepest subduction zone in the world, hasn't caused a devastating earthquake since records began in the 17th century. Investigators needed to know why.
That's the $60,000 question.
They hoped the trench's shallower western edge might provide the answer. Here they found an intriguing chain of underwater hills 2 miles below the surface of the sea. Engineers drilled down into the hills and collected core samples. And when the scientists analyzed the samples, they discovered the hills were actually volcanoes. And they spewed out not lava, but mud. The fine, powdery mud is made up of a soft type of rock that has been ground up in the subduction zone. It seemed this soft rock might explain why there have been no major earthquakes at the Marianas Trench.
Everybody has a sense of what a volcano is, but not all volcanoes erupt igneous rocks. There's some volcanoes that erupt mud, and a certain kind of, an unusual kind of mud in the Marianas is made out of serpentine. And serpentine is a very weak rock, and it can be scratched. with a knife or something like that.
Investigators realized the grinding plates crush the soft rock to form a lubricating mud that prevents large earthquakes. Then the mud bubbles up to the ocean floor, where it forms the strange mud volcanoes found along the trench's western edge.
Other parts of the world, like the Andes or maybe Indonesia, you've got two plates that are grinding together, and one of the plates is quite strong. And it takes a big earthquake to rupture that plate interface. But if these rocks are weak, like they are in the Marianas, where you've got these serpentinites, those are very weak, and it doesn't take much energy at all to get the two plates to glide one past the other.
At last, geologists had discovered what created the Marianas Trench. 50 million years ago, the Pacific Plate slipped under the edge of the Philippine Plate. As it bent and dived into the Earth's mantle, it formed the colossal Marianas Trench. And the plate is still moving. Like a giant conveyor belt, the Earth's crust travels slowly across the Pacific Plate, from its birthplace in the East Pacific Ridge to its graveyard 10,000 miles away in the Marianas Trench. Today, the Pacific Plate's movement can be tracked in real time.
Confirmation has come from GPS technology, where we can actually put a transmitter on an island and come back year after year and actually follow it moving a few centimeters a year towards the trench.
It's devouring the crust at a rate of 3 inches a year, about as fast as a human fingernail grows. Every 4 million years, it swallows an area the size of the United States. By consuming the crust created at the Pacific Ocean Ridge, the ravenous Marianas Trench is the world's largest recycling plant. But there was one remaining and major piece of the puzzle to find. Scientists still didn't know why it is the deepest trench on Earth. They suspected the age of the seafloor at the bottom of the trench may provide the answer.
It turns out there's a really strong relationship between the age of the seafloor and its depth in the water.
In 1999, a team of deep sea drillers returned to the trench to collect core samples.
One great thing about drilling this ocean crust is we actually got pieces of it. So we're holding in our hands here the material that's actually getting subducted at the Marianas Trench, and it turned out to be 170 million years old. So we can say with confidence that's the oldest ocean floor before it's getting swallowed up in the mantle at the trench.
But why is this piece of rock the oldest on the ocean floor?
The seafloor at the Marianas Trench is so old because it's been so long since it was born. So it was born in the equivalent of the Eastern Pacific today, and it's just been going on longer than any other place in the oceans before it's been subducted.
The Pacific Plate is the planet's largest tectonic plate, covering an area 11 times the size of the United States. When crust bubbled up at the ridge 170 million years ago, it was light and buoyant. But as it traveled 10,000 miles across the plate, it cooled and became compact and dense. Over millions of years, the dense crust got heavier and began to sink into the mantle below. Scientists realized that because the crust at the Marianas Trench is the oldest ocean crust, it's also the heaviest and so has sunk deeper into the mantle than any other area of ocean crust. Here at last was the explanation for the trench's extraordinary depth. The picture of the Marianas Trench is almost complete. The investigation into the Marianas Trench has one final puzzle to solve. At the trench's southern end, the sea floor plummets a further 10,000 feet into a 7-mile deep chasm called the Challenger Deep. It's the lowest point on the planet. But so far, scientists have been unable to explain why this one section of the trench is so deep. Now, they believe the shape of the descending tectonic plate may hold the answer.
The Challenger Deep, in addition, is a little bit deeper because of some peculiarities relating to how the slab that's going down is behaving.
A narrow slab of crust has torn away from the Pacific Plate's descending edge.
Well, it's basically got to do with how the slab pushes the mantle out of the way. Where you have a narrow slab, like you have at the Challenger Deep, it can sink almost vertically because the mantle that it's trying to displace can move around out of the way.
Investigators have finally unraveled the mysteries of the Marianas Trench. And in the process, they've made a discovery with implications that stretch far beyond the trench itself. Studying the ocean ridges led geologists to believe that magma welling up at the ridges was pushing the plates apart. But the exploration of the Marianas Trench has changed this idea forever.
People used to think that maybe the magma would kind of push the plates apart. And that idea is largely discounted now.
As the ocean crust travels from the Pacific Ocean ridge to the trench, it changes from a buoyant, red-hot magma into a colder, denser, and heavier crust. The plate's leading edge becomes so heavy that it drags the rest of the plate along behind it.
The heavy, cold plates at the trenches are sinking down into the mantle and pulling the plates apart at the ridges, and the magma just passively fills in the gaps.
The investigation into the Marianas Trench has revolutionized our understanding of how the Earth's plates move. We now know a worldwide network of subduction zones drag tectonic plates around the globe, powering the movement of continents over millions of years, and moving the very Earth we stand on.
The plates that are moving fastest on the Earth are the ones that have all the trenches.
Earth is a blue planet, engulfed by water. But in this desolate chunk of northern Chile, you won't find a single drop. Wedged between the Pacific Ocean and coastal volcanoes to the west, and the Andes to the east, is Atacama, the driest desert in the world. "600 miles long and narrow, on average just 100 miles wide. It's the same size as Iowa. Now, scientists are on a mission to find out how it was made. The investigation begins in the sleepy town of Quiagua. A rare green oasis. Its only lifeline is a stream. Trickling 300 miles from the Andes to the Pacific. It is home to the official government rain gauge, so geologist John Houston has come here to find out how dry the driest place on Earth really is.
This is a pluviometer. It measures the rainfall every day.
Okay.
For Marissa Vera, a government scientist, it's a job with few surprises.
How much rainfall has this instrument recorded?
In the last 15 years, less than 1 millimeter by year.
Less than 1 millimeter a year?
Yes.
Was it every year?
It rains only 3 years.
That's incredible.
Exactly.
So less than 1 millimeter a year.
On average, it rains 3/100ths of an inch a year. It would take a century for Atacama's rainfall to fill a coffee cup. How does this compare with other deserts?
Here we have a cylinder, and I'm going to show you the difference between the amount of rainfall per annum here and the amount of rainfall in other deserts. So if I fill this jar up, right up to about there, that is roughly rainfall that you get in the Sahara. Now if I pour most of that away, we get to that level. That represents what we have in the Mojave Desert, 5 inches per annum. If I pour all that away, except for that little drop in the bottom there, and that's the equivalent of what we have here in the heart of the Atacama Desert. That is such a small amount of rainfall that it means it's the driest place on Earth.
At the equator, moisture-rich air gets heated by the sun and rises. As this hot, wet air flows away from the equator, it quickly sheds its water as rain. By the time it reaches the 2 tropic latitudes, the air has lost nearly all of its moisture, resulting in no rain on the land below. The mystery, though, is why Atacama gets so much less rain than any place else. Scientists hope to crack the case by figuring out how Atacama first formed. On the hunt for clues, Houston travels deep into the true desert. This closely guarded location was discovered during routine mapping by geologists back in the 70s. But the huge significance of their find wasn't realized until 1998. This band of boulders is the single most important clue to Atacama's beginnings. It's a delicate rock called gypsum. A simple test shows how fragile it is.
If I pour a little bit of water on top of that, you will see that it very rapidly falls apart. What's happening here, of course, is that when I'm putting water on this, you see it dissolve. I mean, it's just going to fall apart.
The survival of gypsum as a solid rock tells scientists there hasn't been any heavy rain since the rock formed. So the next step was to date it and figure out when this place became dry. Gypsum can't be directly dated, but by analyzing fossils in the surrounding rocks, the awesome age of the desert was revealed. Atacama is a staggering 150 million years old. 150 million years ago, the Atacama Desert was a seabed covered by ocean waters. But today, some areas in the desert are 2 miles above sea level. In the journey to find out how this happened, scientists take the investigation to the eastern edge of the desert. This strange landscape is the largest geyser field in the southern hemisphere.
We're up at the El Tatio geyser field. You can see around us that there's plenty of hot springs and geysers. There's plenty of steam around, and this is because the air is cool and the water is hot, and so you have a lot of steam and bubbling springs.
The boiling water is being heated deep underground.
The geysers and the hot water that you find up at El Tatio are indications that you have a body of hot rock underneath us. And another indication is you have a bunch of volcanoes surrounding this basin.
The earth here is violently alive. Molten rock erupts onto the surface, forming volcanoes. fiery volcanoes and the boiling geysers are evidence of a turbulent process happening deep beneath the desert. Here, the Pacific Ocean crust is being forced underneath South America, much like a spatula going underneath a pizza. This geological process is called subduction.
You have the Pacific plate colliding with the continental crust, and the Pacific plate is actually heavier and it slides underneath the continental crust. And as it does so, it heats because it gets to a depth of about 60 miles and it becomes molten.
This crucial depth is called a melting zone. Hot molten rock then thrusts upward to form the active volcanoes that ring the El Tatio geyser field. This process gives scientists a hint to what lifted the desert out of the ocean. More clues are found on the opposite side of the desert. Geologists know that these coastal hills were also once volcanoes. Today, they're completely dead, but modern dating techniques show that they first erupted over 195 million years ago. It's a crucial piece of evidence which reveals when the Pacific Plate first began to force its way beneath South America. At that time, the desert, indeed all of Chile, was underwater. Over time, the melting zone was pushed further and further inland, first igniting the coastal volcanoes. As the melting zone passed beneath the desert, it formed new crust, thickening and raising the land. The Atacama Desert slowly emerged. "50 million years ago, this same process began to raise the Andes. Today, the melting zone is 140 miles inland, and the molten rock it produces ignites volcanoes and fuels El Tatio's geysers. But as it passed under the Atacama Desert, it also left behind this. Chuquicamata, the largest open-pit copper mine in the world. Volcanic processes concentrated the copper ore here, but it was the desert's unique climate that locked it in place.
This area of northern Chile produces some of the largest and most important copper deposits in the world, and this is largely due to the very dry climate. Most of the erosion on the Earth's surface is caused by water. So here, where there's so little rainfall and there's very little surface water, there's not very much erosion, and so the copper deposit has actually remained intact.
As a result, this barren wilderness is one of the most valuable pieces of land on the planet.